Hey everybody, this is a quick look at infrared spectroscopy. I'll be moving fairly quickly because students are usually pretty familiar with IR spec, but it is used as a characterizing tool. It can tell us what functional groups are on the compound that we're analyzing by shining infrared light through the said compound. Certain frequencies of that infrared light are absorbed by the bonds without breaking them, and the absorption pattern of the IR spec can tell us what functional groups are on the molecule. Here's a diagram of what a spectrometer looks like and what it does. Basically, we have some sample that we're analyzing, and the spectrometer shines infrared light through that sample, which is picked up by a detector, and then we can analyze the absorption pattern picked up by that detector. As the bonds absorb infrared light, they begin to stretch, twist, or vibrate, and there are a lot of different ways that they can do this, but the important thing is that specific bonds or functional groups absorb pretty specific ranges of infrared light, and that can help us identify which functional groups are on the molecule. You can start memorizing ranges and use handouts like this one, which is in your lab notebook or on Learning Suite, to start learning where these peaks end up. This sheet shows you similar functional groups, for in this case the carbonyl functional group, and it tells you where that peak will show up and what those peaks generally look like. Salt plates are used to suspend the sample to hold it in the infrared spectrometer. And the reason we use salt plates is because they don't absorb the same range of infrared light as covalent bonds do, so they won't cause any noise in the peaks that we are trying to observe. So here are what the salt plates kind of look like. We take one and add our product to it. In this example, we're looking at a liquid product. You can do the same things with a solid product. It's a slightly different technique. In this video, I'll be focusing on liquid samples. But you add a droplet of liquid and then place the salt plates together, which will suspend the liquid in between them. And then you can put those salt plates into a holder, which will then be placed into the spectrometer. And I'll show a video of me actually doing this so you can see what it looks like. When an IR spec is run, it's going to pick up anything that the infrared light goes through. So this includes molecules in the air, carbon dioxide that people are breathing out in the lab. So we're going to get quite a bit of noise, and this is what it looks like when it's run through an empty compartment. We can see different things being picked up from the air. And then if we run that along with our sample, we definitely see the peaks from the molecule that we're trying to analyze, but we get a lot of extra noise from all this stuff in there. So what we do is we run a background of an empty compartment, and then the spectrometer will get rid of those peaks so that when we analyze our molecule, we only get the absorption for the bonds in that molecule. We keep the salt plates in a bottle with desiccant salt in it, which absorbs water. And we want to do this because the salt plates are obviously made out of salt, and ionic compounds dissolve in water. So if exposed to water for too long, the salt plates will start to dissolve. And then this is what these salt plates actually look like. For this video, I'll be using isoamyl acetate, which is the product from the Fisher Certification Lab, so you can use this video to fill out your IR spec for the first lab. I'll take the salt plates and add the liquid product onto one of them, just a droplet of it, and then place the salt plates together, and this will suspend the liquid in between them. This is the program to run the IR spec. I'm going to go ahead and run it with an empty chamber without any sample in it, just so you can see what the background would look like of running the IR spec with nothing but air in there. And like we saw in the slides earlier, this is what the background looks like, an empty chamber with nothing but the molecules in the air. Now I'll run it with the sample in the spectrometer so you can see what it would look like with the compound and all the background noise, which looks like this. So we're seeing additional peaks from the actual compound that we put in there, but we want to get rid of all of the extra noise. To do that, I'll remove the sample and run it again, this time collecting a background, which basically just tells the machine that whatever it's picking up is actually not wanted, and therefore will remove those peaks when we run the sample again. So now we can put the compound back into the spectrometer and we'll collect our sample once again. This time it'll remove all of the background noise, leaving just the peaks from our compound that we want to see. To analyze the peaks for this compound better, I'm going to click on the Find Peaks function, which places numerical values for the wave numbers of each peak, and I'll just click high enough to include the pertinent peaks for this molecule, and after that we'll have a very clean IR to now analyze. Now I just want to quickly show you some of the common mistakes with infrared spectroscopy. For example, if we added too little of our product to the salt plates, which would end up looking something like this. We still see the peaks that we would expect to see on our compound, but they're just very small and would be hard to analyze. Here's a look at what would happen if we added too much product. Now with liquid samples, it's not really an issue. With solid samples, you start seeing a lot more problems with too much sample. You see all of the absorption way lower on the screen. Here's a look at a sample with some water contamination. We still see the pertinent peaks, but we see a big OH peak on the far left there and some other noise. But here's what it would look like if we had mainly just water contamination on our salt plates. To clean off the salt plates once we're done, we don't want to use water because that'll start to dissolve them. So we're going to rinse these salt plates with the product on them using acetone, and we'll rinse them off into this giant Erlenmeyer flask, which has a funnel on top of it. So I'll just quickly rinse both sides with that acetone, which should easily remove any organic product that would be left on them. Then I'll wipe them off real quick and place them back into the container for future use. For the rest of the video, I wanted to go over and label the IR for the Fisher Esterification Lab, the product for that lab being isopentyl acetate. So let's take a look at the functional groups. We have all of the carbon-hydrogen bonds for sp3 hybridized carbons, which show up right here, so we can label that like so. Then we have all of the carbon-carbon single bonds, which show up around 1370 and 1450-ish, so we can label those peaks. Now these peaks aren't as identifying as others because this is organic chemistry and most molecules are going to have carbon-carbon and carbon-hydrogen bonds, so they're not going to be as useful as some of the other peaks that indicate more unique functional groups, but it's still good to know where they show up. Now let's take a look at the carbonyl, or the carbon double bonded to an oxygen. Its peak shows up around 1700 to 1750, and it's going to be a nice sharp peak that's very identifiable. This peak is your friend. It usually stands out pretty well from all of the other peaks and can help you identify functional groups that have carbons double bonded to oxygens. Now let's take a look at the carbon to oxygen single bonds, and on this molecule we actually have two. On this side of the ester we have a carbon-oxygen single bond in which the carbon is sp3 hybridized, so we would expect to see its peak around 1050 to 1150, which we see here, so we can go ahead and label that. And on this side of the ester, we have a carbon-oxygen bond where the carbon is sp2 hybridized. So we would expect to see its peak around 1250, which we see here, so we can go ahead and label that. Lastly, we have a little bit of an OH peak showing up here, but we don't have an OH group on this molecule, meaning that that peak has to be coming from some kind of contamination. So we'll go ahead and label that as OH contamination. And that's it. That is how we run IR spec in this lab, and this is how you should label each of the IRs given to you for each of the experiments.